Far beyond the outer planets in the deep and silent dark, a machine built with 1970s technology is still talking to Earth. It carries less onboard computing power than a modern greeting card, its signal weaker than a whisper by the time it crosses the distance separating it from us, and yet, as of this year, it's still transmitting real, usable scientific data across roughly 12.9 billion miles of space. Voyager 2 has now been operating for 49 years, and what it found on the way out of our solar system wasn't the clean, simple boundary scientists expected. It was something considerably stranger. The mission began during a genuinely rare planetary alignment in the late 1970s, one that occurs roughly once every 175 years, letting a single spacecraft use the gravity of each outer planet in sequence to slingshot toward the next, a trajectory NASA couldn't have attempted otherwise. Taking advantage of that window, NASA launched 2 spacecraft in 1977, Voyager 1 and Voyager 2. Both were designed to operate for roughly 5 years. Both have now operated for nearly a decade past their 40-year mark. Voyager 2 flew past Jupiter, then Saturn, then went on to become the only spacecraft in human history to fly past both, Uranus and Neptune, a feat no other mission has repeated in the decades since. After completing that planetary tour, it kept going, pushing outward into territory nobody had ever directly measured before. Eventually, both Voyagers approached the outer edge of the Sun's zone of influence, a vast region called the heliosphere. This enormous bubble, inflated by the constant outward pressure of solar wind and the Sun's magnetic field, surrounds our entire solar system and acts as a kind of shield against the harsher radiation environment of interstellar space. For decades, scientists expected a sharp, clean boundary at its outer edge called the heliopause, a place where instruments should register an obvious, dramatic shift. Particle counts should jump, and the direction of the magnetic field should flip cleanly from solar to interstellar. When Voyager 1 crossed into this region in 2012, the data coming back was genuinely confusing. When Voyager 2 followed, and crossed its own version of that same boundary in November 2018, it confirmed the same underlying mystery rather than resolving it. Some indicators shifted the way models predicted. The magnetic field, crucially, did not flip cleanly the way the old models assumed it would. That's a genuinely significant finding, and it's worth sitting with directly. Instead of a sharp dividing line separating solar from interstellar, the actual boundary behaves more like a blurred, complicated transition zone, where forces from inside and outside our solar system visibly mix and interact, rather than cleanly handing off from one to the other. Rather than a clean seam, there's turbulence and overlap, and pinning down exactly where one region ends and the other genuinely begins turns out to be considerably harder than any pre-Voyager model assumed. Further analysis deepened the puzzle rather than resolving it. Researchers expected the size and shape of the heliosphere to shift meaningfully depending on the Sun's current level of activity, since solar wind pressure should expand or contract that bubble over time. Yet both Voyager spacecraft crossed their respective boundaries at broadly comparable distances from the Sun, despite genuinely different solar conditions at the time each crossing happened. That's a real documented discrepancy with the simpler models, and it suggests the heliosphere's actual structure may be considerably more dynamic and less predictable than the tidy diagrams in textbooks imply. Meanwhile, Voyager 2 keeps operating under conditions that would have ended almost any other mission decades ago. Its power source, a radioisotope thermoelectric generator that converts the heat from decaying plutonium into electricity, loses roughly 4 watts of output every single year, a slow, permanent decline that can't be reversed or refueled. According to NASA's own mission updates, engineers have already had to shut down heaters and other non-essential systems just to keep the spacecraft's remaining science instruments powered. As of right now, in mid-2026, Voyager 2 is down to 3 of its original 10 science instruments, having lost its plasma. Science experiment in October 2024, and its low-energy charged particle instrument in March 2025. Its cosmic ray subsystem is scheduled to be powered down sometime this year as part of the same ongoing power conservation plan. Every single one of these shutdown decisions is treated as potentially permanent, because once an instrument this old goes dark, there's no guarantee it can ever be brought back online again. Before we get into exactly what Voyager 2 found once it actually crossed into interstellar space itself, the region genuinely beyond the boundary we just covered, and why that data turned out to be even stranger than the crossing itself. I want your take. Does knowing this spacecraft is still sending back real scientific data using 1970s era hardware, nearly 5 decades after launch, change how you think about the pace of modern technology by comparison? Drop your answer below, and subscribe now, because Section 2 is where Voyager 2's discoveries get genuinely more surprising. Crossing into interstellar space did not make Voyager 2's mission simpler or quieter. If anything, the data coming back afterward became even more genuinely puzzling than the boundary crossing itself. Beyond that invisible edge lies interstellar space, the vast region between star systems filled with particles, magnetic fields, and radiation that originate from far beyond anything the sun directly influences. Before Voyager 2 actually reached this region, many researchers pictured it as relatively calm and uniform compared to the turbulent environment closer to the sun. The data told a genuinely different story. Instead of a smooth, steady transition, Voyager 2's instruments detected real variations in plasma density, shifts in particle energy, and subtle fluctuations in the surrounding magnetic field, all pointing toward a region considerably more dynamically active than the earlier, simpler models predicted. One of the clearest, most striking findings involved cosmic rays, high-energy particles traveling at nearly the speed of light, many of them originating from distant supernova explosions elsewhere in the galaxy. As Voyager 2 moved farther from the sun's protective influence, the density of these particles increased significantly, confirming directly that the heliosphere genuinely does function as a real physical shield, meaningfully reducing the intensity of cosmic radiation that ultimately reaches the inner solar system, including Earth. That's not a small finding. It's direct physical confirmation of a protective effect scientists had theorized about for decades, but never actually measured directly from inside the transition itself. Even this discovery came with its own layer of complication, though, which is exactly the pattern that keeps showing up throughout this entire mission. The rise in cosmic ray density wasn't perfectly smooth or steady. There were real variations, sudden shifts that hinted at invisible structures or waves passing through interstellar space itself. Structures nobody had directly detected before Voyager's instruments happened to be sitting in exactly the right place to register them. That variability suggests this region isn't empty or still in the way older models assumed. It's filled with motion and hidden activity that current theoretical frameworks are still working to fully explain. Temperature produced another genuine surprise. Based on earlier models, scientists expected the region just beyond the heliopause to be extremely cold and relatively simple in its underlying structure, essentially a quiet, frigid void. Instead, Voyager 2's instruments detected plasma temperatures considerably higher than those pre-mission models predicted. That single finding opened up real, still unresolved questions about exactly how energy gets transferred and distributed out in interstellar space. Some researchers have proposed that shock waves or ongoing interactions between solar material pushing outward and interstellar material pushing back could be generating localized pockets of heating in this transition zone. Others have suggested magnetic turbulence itself might be playing a larger role in redistributing that energy than anyone previously assumed. Either way, every serious explanation on the table agrees on one central point. This region is nowhere near as simple or as thoroughly understood as the pre-Voyager textbooks confidently described it. Communication itself has become its own genuine engineering challenge as the spacecraft has continued moving farther away. Signals from Voyager 2 currently take roughly 19 hours to reach Earth, traveling at the literal speed of light across billions of kilometers of empty space, and they arrive faint enough that only the massive specialized dish antennas of NASA's Deep Space Network are sensitive enough to detect them reliably. Despite that distance and that signal weakness, the spacecraft continues sending back real data in small, carefully managed increments, essentially a distant, persistent whisper arriving from the practical edge of human technological reach. Engineers on the ground have to make careful, deliberate decisions about exactly which systems stay powered and which get shut down permanently, because once a specific instrument goes dark on a spacecraft this old and this far away, there's no realistic path to turning it back on again. What makes all of this genuinely remarkable when you actually sit with it is that Voyager 2 was never designed or built for a mission of anything close to this length. Its systems have endured nearly 5 decades of extreme cold, constant radiation exposure, and the slow, steady degradation that comes with simply existing in deep space for that long. And it continues functioning anyway, continuing to provide direct physical measurements that no modern spacecraft has replaced or superseded, because no other spacecraft has traveled far enough or lasted long enough to occupy the same physical position in space that Voyager 2 currently holds. As scientists have worked through this incoming data over the past several years, they've had to genuinely rethink some long-standing assumptions about exactly how our solar system interacts with the broader galaxy surrounding it. The old idea of a simple, clean boundary separating our system from everything else has been replaced with something considerably more complex, more genuinely dynamic, and less predictable than the pre-Voyager consensus assumed. There's also a deeper, genuinely open implication sitting underneath all of this, one that extends well beyond our own solar system specifically. If the boundary of our own heliosphere turns out to be this blurred and this complicated structurally, what does that suggest about the equivalent boundaries surrounding other star systems scattered across the galaxy? Do other stars generate similarly turbulent, similarly unpredictable protective bubbles of their own? Are some of those bubbles meaningfully stronger or meaningfully weaker than our own sun's? And given what we now understand about how much a heliosphere-like shield can influence the radiation environment reaching a system's inner planets, could that specific structural difference meaningfully affect the actual potential for life to exist and persist in other systems entirely? Before we get into how NASA is actively managing Voyager 2's rapidly dwindling power supply right now, and just how much longer this genuinely irreplaceable mission might realistically continue operating, I want your take. Does the idea that other star systems might have their own uniquely turbulent, unpredictable protective boundaries change how you think about the broader search for habitable worlds elsewhere? Drop your answer below and subscribe now, because Section 3 is where we get into exactly how NASA is fighting to keep this 49-year-old spacecraft alive. Let's talk directly about the engineering fight currently underway to keep Voyager 2 alive, because it's genuinely one of the more remarkable ongoing efforts in modern spaceflight, precisely because there's no way to service, repair, or refuel a spacecraft sitting nearly 13 billion miles from Earth. Every decision has to be made remotely, communicated across a roughly 19-hour one-way signal delay, and treated as effectively permanent the moment it's executed. Both Voyager spacecraft are powered by radioisotope thermoelectric generators, devices that convert the steady heat released by decaying plutonium-238 into usable electricity. That decay process can't be paused, refueled, or reversed, and it means both spacecraft lose roughly 4 watts of available power every single year, a slow, entirely predictable decline that mission engineers have been managing for decades. Back in 2023, NASA engineers found a way to tap into a small reserve of backup power originally set aside as part of an onboard voltage regulation safety mechanism, a move that let them postpone shutting down a science instrument on Voyager 2 by several years longer than originally planned. That single engineering decision is a big part of why the spacecraft is still transmitting today, rather than having already gone silent. But that reserve power was always a temporary bridge, not a permanent solution. And the shutdowns have continued on a carefully pre-planned schedule the Voyager science and engineering teams agreed on years in advance, prioritizing exactly which instruments provide the most scientifically valuable data for the specific region of space each spacecraft currently occupies. Voyager 2 lost its plasma science experiment, the instrument that measured how much plasma flows past the spacecraft and in which direction, back in October 2024. It lost its low-energy charged particle instrument in March 2025. As of this year, according to NASA's own mission updates, its cosmic ray subsystem is scheduled to be powered down as the next step in that same ongoing sequence. And NASA has also begun testing something engineers have internally nicknamed the Big Bang Plan, a coordinated swap of older, higher power components for lower power alternatives, specifically designed to stretch the spacecraft's remaining electrical budget even further. Voyager 2 is testing that exact procedure this year, with Voyager 1 expected to follow if the test holds up successfully. If everything goes according to the current plan, NASA's own engineers believe both Voyager spacecraft could continue operating with at least one functioning science instrument each into the 2030s. An extraordinary outcome for hardware designed in the 1970s for a mission originally planned to last just 5 years. That's not a guarantee, though, and NASA has been direct about that uncertainty. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, put the core tension plainly in a recent mission update. The team wants to keep both spacecraft operating as long as physically possible, but electrical power is genuinely unavoidably running. Low, and without these deliberate shutdown decisions, both Voyagers would likely have had only a few additional months of operation before mission engineers would have had to declare an actual end of mission. There's something worth sitting with in how methodical this entire process has actually been, because it's easy for headlines to frame every individual instrument shutdown as a dramatic, unexpected crisis, when in reality, this has been a carefully sequenced, years in advance plan executed with remarkable precision. The order in which specific instruments get powered down wasn't improvised in a moment of panic. It reflects a genuine, considered judgment call about which measurements remain scientifically valuable for the specific region of space each spacecraft currently occupies, weighed directly against the spacecraft's steadily shrinking electrical budget. That's a genuinely different, more sober picture than NASA is racing to save a dying spacecraft implies, even though the underlying stakes, the eventual permanent loss of humanity's only 2 direct physical presences in interstellar space, are exactly as significant as that dramatic framing suggests. It's also worth being honest about what actually happens once Voyager 2 finally does lose its last functioning instrument, whenever that eventually occurs. The spacecraft's mission, in terms of active scientific data collection, will end, but the spacecraft itself won't stop sting, and it won't stop moving. It will continue drifting silently through interstellar space for what amounts to an almost incomprehensible span of time, carrying its golden record, the phonograph disc containing sounds and images meant to represent humanity Whatever, or whoever, might eventually encounter it for potentially billions of years into the future, long after every human being currently alive and likely every human civilization, as we'd currently recognize it, has come and gone. That's a genuinely strange, almost paradoxical thing to sit with. A machine built with less computing power than a modern car key, one that's already fundamentally reshaped our understanding of where our solar system actually ends and interstellar space genuinely begins, is simultaneously running out of power in real, measurable, predictable increments, while also being built to physically outlast every single one of us by a margin so large it's genuinely difficult to process. Before we bring this all together in the final section and look at exactly what Voyager 2's remaining time might still teach us, and why its discoveries matter for understanding star systems well beyond our own, I want your take. Given that this spacecraft may keep operating scientifically into the 2030s, but will then drift silently for billions of years. Afterward, does that timeline change how you think about what mission success actually means for something like this? Drop your answer below and subscribe now, because the final section brings together everything Voyager 2 has taught us, and what its remaining years might still reveal. Let's bring this all together, because what Voyager 2 has actually revealed, patiently across nearly 5 decades, adds up to something considerably more significant than any single data point on its own. This isn't a story about one dramatic discovery. It's a story about a slow, methodical unraveling of assumptions that scientists had confidently held for generations, delivered by a machine that was never supposed to survive long enough to do it. Here's the complete, honest picture. Voyager 2 confirmed, directly and physically, that the heliosphere genuinely does shield the inner solar system from a meaningfully higher dose of interstellar cosmic radiation, exactly as theorized, but it also revealed that the actual boundary of that shield isn't the clean, sharply defined edge older models assumed. It's a blurred, turbulent transition zone where solar and interstellar forces visibly overlap and interact, rather than handing off cleanly from one to the other. It found that both Voyager spacecraft crossed their respective versions of that boundary at broadly similar distances, despite meaningfully different solar conditions at the time, a real discrepancy with the simpler predictive models. And once fully inside interstellar space, it found plasma temperatures higher than expected, cosmic ray variability that hints at invisible structures passing through space that current models are still working to fully explain, and an environment considerably more dynamic than the cold, quiet void many researchers pictured before Voyager actually got there to check. None of these are dramatic, singular headline moments in the way a single stunning photograph might be. Together, though, they represent something genuinely important, a real, physically measured correction to how scientists understand the specific place where our solar system's influence ends and the broader galaxy genuinely begins. That correction didn't come from a supercomputer or a next-generation space telescope. It came from a spacecraft built with technology from the 1970s, one that's been losing roughly 4 watts of power every year for nearly 5 decades straight, and is still, right now, in 2026, sending back real, usable data from further away than any other human-made object has ever traveled. And that data collection isn't finished yet. NASA's current power conservation plan, including the recently tested Big Bang component swapping procedure, is specifically designed to keep at least one science instrument functioning on each Voyager spacecraft into the 2030s. That means Voyager 2 may well continue measuring the magnetic fields and plasma waves of interstellar space for several more years, yet adding incrementally to a dataset that quite literally cannot be replicated by any other current or currently planned mission, since no other spacecraft occupies anything close to the same physical position in space. And building a genuine replacement mission from scratch would take decades before it could even begin approaching the same distance. Here's the deeper question this entire mission leaves us with, and it's genuinely bigger than Voyager 2 itself. If the boundary of our own solar system turned out to be this complicated, this blurred, this dynamically unpredictable, once a spacecraft was actually there to measure it directly, what does that suggest about the equivalent boundaries surrounding other stars scattered throughout the galaxy? Every star with its own version of a heliosphere is, in effect, running its own version of this exact experiment, shielding or failing to shield its own planets from the broader galactic environment, in ways we currently have no direct way of measuring from Earth. Voyager 2 gave us our only direct physical data point for how this process actually works in practice rather than in theory, and that data point alone has already forced real revisions to how astronomers model this specific structure everywhere else in the galaxy. There's something genuinely worth sitting with in how this entire story closes too. Voyager 2's active scientific mission will eventually end whenever its last functioning instrument finally loses power for good. But the spacecraft itself won't stop moving. It will keep drifting silently through interstellar space, carrying its golden record for a length of time so vast it's genuinely difficult to hold in your head, likely outlasting every trace of the civilization that built it. A machine with less computing power than a modern car key has already reshaped our understanding of where our solar system genuinely ends, and it's built to keep traveling long after that correction has been fully absorbed into textbooks, and long after those textbooks themselves have been rewritten again and again by whatever comes next.